In this video, I'm going to show you how to use your TI 84 Plus calculator to answer questions involving hypothesis testing with T distributions. So there's going to be two questions that use hypothesis testing, and we'll be using the p-value method. The first question will be one sample, the second question will be two samples, and then the third problem we'll look at will involve a confidence interval with the t distribution. So all of these you can get pretty quickly on your calculator. The university that I teach at, you need to know how to do this on a calculator. So that's what we're going to do. Now, you use the t distribution when the sample size is small, so your sample size is less than 30, and the population standard deviation, sigma, is unknown. Now, what happens that I'll see with most students is they'll see these words, and they'll think because they see those words that they've been told what sigma is, when in fact they're being told the sample standard deviation. So that's the biggest pitfall students seem to fall into, thinking that sigma is known when it's not, and so they don't use the t distribution. Alright, so now the shape of a t distribution is bell-shaped like a normal distribution. It tends to be flatter, and so the tails are larger. Okay, but let's have a look at our first example. A university professor, so let me just scroll this up a little bit. Okay, a university professor claims that students study an average of 10 hours for their finals. However, based on your experience, you believe that students may study significantly more than 10 hours for the finals. So you decide to test this by doing a survey, a sample of 15 students, so n is equal to 15. And you find that in this sample that they study an average, so our parameter here is going to be the mean, of 12 hours. So my sample mean is 12 hours. And here we go with a standard deviation of 3 hours. This is not sigma. This is the standard deviation of your survey, of your sample. If it was a population standard deviation, you'd be told something like, you may assume that the standard deviation for all students studying for a final is 3 hours. But we haven't been given that language. This is part of the sentence that's giving you the sample data. And so nowhere are we told what the population standard deviation is, so sigma is unknown, and so we're going to use a t distribution. Now, we only have one sample here. Okay, so is there significant evidence to suggest that the average study time for students is greater than 10 hours? So the claim that we want to test, our original claim, is that for all students their mean study time is greater than 10 hours. That's our original claim. Now, the null hypothesis is always equality. And then the alternative hypothesis, well, you look at the symbol in the original claim, and if it's allowed, you keep it in the alternative hypothesis. The alternative hypothesis, you're allowed to use the not equal, strictly greater, and strictly less than symbols. So this is a strictly greater than symbol. We're allowed that, so we're going to keep it. So we would have a right-tailed test there if we were doing the critical value method, which we're not, because it's a calculator. We're going to use the p-value method because it's just going to spit out the p-value to us and we don't have to calculate it. Okay, so based on this, I'm going to click on Stat, and then I'm going to come over here to Tests, and I want to do a t-test with one sample, so I'm just going to scroll down here to the second selection, t-test. Now, I've got old data in here, and I can just overwrite it. Now, the very first row there, it says input. If I was given a chart of raw data values, then I would select data, but you can see here I was given summary statistics. So it's actually flashing on summary statistics, so that's what I want highlighted. Now in the next row, we've got what is your value for the null hypothesis, and in the null hypothesis we have mu is equal to 10. So again, I'm just going to overwrite it even though the answer was 10. And now it wants to know what was your sample mean. So for this problem, the sample mean is 12. And so I'm just going to overwrite this. This is old data. And what was your sample standard deviation? My sample standard deviation was 3. Now N is, well, what is your sample size? It's 15. Now we come to the next line, and it wants to know what was the symbol used in the alternative hypothesis. And we had the strictly greater than symbol, so that's the one that needs to be highlighted. So now I'm ready. I'm going to go here to calculate. That T is your test statistic, but I don't need it. I'm going to use the p-value method, so this is my p-value. And I'm going to take that to 4 decimal places. So that 6 is going to bump that up to 9. So my p-value is going to be 0.0109. And my alpha, well, your alpha is your significance level, and it's always in decimal form. It's never in the percentage. So my alpha is 0.05. Now, the number 0.01, yada, 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 is smaller than the number 0.05. So our p-value is smaller than alpha. So the p is low, the null must go. So we are, because of this, we are going to reject the null hypothesis. Okay, so what I need here for my chart is what I've got circled there. Now I can have the wording of the final conclusion. So the symbol in the original claim was the strictly greater than symbol. Okay, so we're coming here. We had the strictly greater than symbol, and then we rejected the null hypothesis. And so this is going to be the wording of the final conclusion. So if it's kind of small to read, it says there is enough evidence to support the claim. So now I'm going to write the final conclusion. There is enough evidence to support the claim that the average study time for students is greater than 10 hours. So you have to write it in English, not with any symbol. So like a layperson could understand it. So in black there, that is the wording of my final conclusion. Okay, so that's the end of the first example. Now, if you needed to see this, if it's hard to read it, let me make it a little bit bigger. Okay, so you might want to take a screenshot. Put this on pause and take a screenshot. This is how you get the wording of the final conclusion. Okay. All right, let's go on to the next one. Now we're going to have 2 samples. And this scenario, this example is drug effectiveness. So a pharmaceutical company is developing 2 drugs to improve focus and concentration to test whether there is a difference in effectiveness between the drugs. Okay, so these words are going to tell us what to use in our symbolic form for the original claim. But we have 2 samples here. So in the first sample, the sample size is 12, and the sample mean, because they use the word average, is 8.5. for the effectiveness score, and the sample, because they're talking about a sample. So just because you see the word standard deviation there, that does not mean you automatically put that that is sigma. This is the standard deviation of the sample. And for the second sample, the sample size is 10. The average effectiveness score for the second sample is 7.2, and for the second sample, the standard deviation is 1.8. Now, we are given no information at all about the population standard deviation. So sigma 1 and sigma 2 are unknown. And even though they're unknown, we still have not been given any information if they're related, if they're the same. So we cannot assume that they are the same. So sometimes you won't have any information on what sigma 1 and sigma 2 are specifically, but they'll say you may assume that the two population standard deviations are the same. We have not been given that information. And that's important with what we're fixing to do. Okay, so since sigma 1 and sigma 2 are unknown, we have a t-distribution and we have two samples. And we want a t-test with two samples. Okay, so I'm going to get out of this window and then I'm going to click on Stat and come over here to Tests again. And I'm going to scroll down to number 4 because that's what I want, a two-sample t-test. Now again, I have been given summary statistics. So that's what we want highlighted, and that's what we've got there. So my sample mean, so these didn't come in the same order that the calculator's asking them for, but that's okay. The sample mean for my first sample is 8.5. The sample mean, the standard deviation for my first sample is 2.1. And my first sample has size 12. Then the sample mean for my second sample is 7.2. And the sample mean, the sample standard deviation for my second sample is 1.8. And then my second sample has 10. Size of 10. Okay, now let's see what the original claim is. So the original claim in symbolic form is that the population mean effectiveness score between the two, do they differ? So differ means that they're not equal. Now you might look at this and say, oh, well, these two scores were different, so of course they're going to be different. No. They were different in the two samples, and what we need to know is that difference significant? If it's not significant, then you say, okay, they didn't have exactly the same effectiveness score, but there's no significant difference between the two. All right, so our null hypothesis, as always, is going to be that they're equal. And now the alternative hypothesis, sometimes it's with a capital A, sometimes it's with a 1, depending on your textbook, so I'll just write this one with a 1. You look at the original claim. That symbol is allowed in the alternative hypothesis. You can have not equal, strictly greater than, or strictly less than, so you keep it. So if you were doing the critical value method, it would have a two-tailed test, but we're not doing the critical value method, okay? All right, so I'm going to come here on the calculator, and on this line they want to know what was the symbol that you used in the alternative hypothesis. And of course we want to highlight the not equal to mu2. All right, so that one's highlighted now. Now it comes to pooled, and this is why we had to recognize that we were not told, even though we didn't know the two population standard deviations, we weren't told that they were the same. And it's only if you're told that they are the same, that you can assume they are the same, that you would pool. Since we cannot assume they are the same, we do not pool. So we're going to highlight no. And now we're going to calculate. And I'm going to use the p-value method. So this is my p-value, which I'll take to 4 places. So the p-value, and then I'm going to write alpha. My p-value is 0.1337. And alpha is your significance level, and alpha is 0.05. Okay, now the number 0.1 yada 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 is a bigger number than 0.0 yada yada yada. So this is a bigger number, so my p-value this time is bigger than alpha, and that means we failed to reject the null hypothesis. So the two important things I want are the symbol in the original claim and whether or not I rejected the null hypothesis, because I come here and my symbol in the original claim was the not equal symbol. Okay. Now I failed to reject the null hypothesis, and that means I come down to this statement of the final conclusion, and that says there's not enough evidence to support the claim. And so this is what we would write in black. There is not enough evidence to support the claim. That the two drugs differ in their effectiveness. So the two drugs are significantly different. In effectiveness. So yes, in the experiment, they weren't exactly the same, but that difference is not significant. So it doesn't matter which drug you take, A or B, you should see the same results. Okay, so now let's go on to one that has a confidence interval. A survey of 25 athletes. So N is equal to 25. Find that they work out an average of 6.5 hours a week. So my sample mean is 6.5. The standard deviation is 1.2 hours. Now that is talking about the sample standard deviation. If that was the population standard deviation, it would say you may assume that the standard deviation for all athletes working out is, or you may assume that the population standard deviation is. It has not told us that. They're only referring to the sample. So sigma is unknown. So again, we're going to have a t distribution. It's one sample. And they want us to calculate a 90% confidence interval to estimate the average weekly workout time for all athletes. Okay, so let's get out of here, second mode, and then I'm going to press stat. I'm going to scroll over to tests, and I want an interval, a confidence interval, and since it's a t distribution, I want t interval. Now notice here it's not on the screen, so just keep scrolling. Scroll. There it is, t interval. That's what I want. Now again, we have been given summary statistics. We were not given the raw data, so that's what we want highlighted, which it is. Okay, the sample mean is 6.5, and the sample standard deviation is 1.2. The sample size is 25. And the confidence level is 90%, but that has to be in decimal form, so 0.9. And this was left over from a previous problem, so yours might be blank if it's the first time you're using this command, or it might have 0.95 or something from a previous problem. And then I'm going to come down here and calculate. Okay, so the way that we can interpret this is we are 90% confident that the average weekly workout time for all athletes which we'll call mu is, well, mu is going to be between 6.0894 hours and 6.9106 hours. Okay. All right. So, excuse me, I hope that gives you enough examples where we've used the t-distribution and how to use your TI-84 Plus calculator to get your results. But the important thing is you have to write up in black what your conclusions are. So you have to actually know what you're talking about as far as the conclusions go. So thanks for watching this video, and I'll see you on the next video.